morning, everyone. And so I'm going to coordinate the next two sessions. So may I take this opportunity to thank to our staff and students who have contributed to organizing this beautiful seminar. So we have had really exciting presentations so far, and I hope you have enjoyed. So next presenter is Ezgi Bal Yetim. So the title of her presentation is Impact Behavior of Precast Concrete Seawall Panels Reinforced with GFRP Bars. Ezgi, a PhD student at the Center for Future Materials, University of Southern Queensland, specializes in marine infrastructure, specifically reinforced concrete seawall with a glass fiber reinforced polymer. She also completed her master's degree at UniSQ, focusing on coastal floodways during extreme events, dedicated to enhancing coastal resilience against climate change and hazards. Her work focuses on the impact behavior of precast concrete seawalls using non-corrosive GFRP bars, addressing the need to understand the impact behavior of seawalls for varying design parameters. So, Ezgi, you have 15 to 20 minutes for your presentation, and then we will have 10 to 15 minutes for Q&A. So just can I ask kindly ask the attendees, please, if you have any question, please type in the chat. Then after the presentation, I will read it and Ezgi can attend the questions. Thank you.
Thank you very much, Hadi, for your introduction. Let me share my screen for my presentation. I hope everyone can hear me from my computer.
Yes, we can.
Okay, thanks for confirmation, Hadi. So let me open my presentation. Okay, can everyone see my screen, like my presentation? Okay, thank you. I would like to introduce myself. My name is Ezgi Bal Yetim, and I'm a Doctor of Philosophy student in the Center for Future Materials. And my supervisors are Professor Ellen Malino, and I would like to thank them at the beginning of this presentation for their ongoing support and help during my PhD journey, and Dr. Omar Alajarme and Associate Professor Veena Lokuch. And I would like to also mention my industry partners. They are Advanced Queensland and Beyond Materials Group and Sunshine Coast Council. So today I would like to talk about my PhD progress so far about the impact behavior of precast concrete seawall panels reinforced with GFRP bars. I would like to start with acknowledging the country. UNESCO acknowledges the First Nations of Southern Queensland and their ongoing connection to country, lands, and waterways. We pay deep respect to elders, past and present. I would like to give you a general overview of what I'm going to talk about today. The first section will be about the introduction, and then I will talk about the research gap and significance, and then objectives and literature review, methodology, and results and discussion section. So as you can see now from these pictures, the climate change and global warming are a very great concern in Australian coastlines, and they usually cause the rises in global temperatures, and they cause storm events and sea levels, rises in sea levels. So that causes, it brings two major problems. The first one is the corrosion of the steel and like the debris problem. As you can see from these pictures, the first image shows a seawall damage in Sunshine Coast taken in 2013 in Mooloolaba. So this seawall has been damaged by these storm events and the rock storms just went all over the place, and that was one of the seawall damages they mentioned in their official website. And also we have in 2011 we had a very big flooding event occurred in Australia, and that caused some severe damage to the seawalls due to the debris and vessel loading. And I would like to also mention this corrosion problem. As you know, seawalls can be in different types, like vertical seawalls, rock seawalls, and reinforced seawalls with steel. Usually, the steel ones are having a corrosion problem and cracks over the time. And usually the problem with the rock seawalls are they are easily washed up, like during the storm events, because they like little stones that they can be easily move away. So this is also taken from the Sunshine Coast City Council after a storm event. And that's also from New South Wales. It can be seen that the severe damage on the shoreline due to the storm damage and flooding events. So this is why we want to focus on seawalls, especially as a structural property. So I would like to also talk about in terms of the cost of the replacement and damages in Australia. So usually, if the impact can be in any form, due to the vessel incidents, they result in severe damage to infrastructures, and usually 24%, almost 24% of these incidents are causing due to this vessel crashing or incidents. And according to impact failure and probability of occurring, although this is very low, but it can have a very significant damage, which is at the contact. Contact significance is around 57%. So based on this information, I made some research about the costs, and the replacement cost is expected to be around 226 billion by 2100 due to the sea level rises of 1.5 meter. And in Queensland, assets only expected to be affected from these storm events and sea level rises and flooding is around 71 billion. Also, for the corrosion related problems, they are having 15 billion spendings every year for to fix these corrosion related problems. So that's why it's necessary to understand the behavior of GFRP-reinforced concrete seawalls, reinforced with GFRP instead of steel, and understanding their behavior under this extreme loading conditions, such as impact. So why we also have chosen this project, because no one has ever done GFRP reinforced seawalls under impact behavior. This is why we have selected some parameters, and we have identified this gap in the knowledge as well, that usually they don't have this GFRP reinforcement in seawalls, and this is a new and initiative research area. Based on that, we selected some parameters to focus on the performance under impact loading, which is, as you know, the impact loading is dynamic loading, and it requires like a dynamic analysis due to the lack of design guidelines as well. We have selected some design parameters that to analyze the impact behavior of concrete seawalls, which are still unknown, such as drop height or reinforcement configurations, such as like steel, such as the bar spacing, bar diameter, and drop height. Drop height is one of the most important ones because it's about the impact energy, and impact energy means it's about the resistance to structure that gives us information about the structure's toughness. So based after this these studies, I will focus on numerical and parametric study with different parameters after the verification. But currently in this particular presentation, I will just talk about the drop height. That's my first objective. And then I will try to see the chance to create some prediction equations for the impact behavior of seawalls. So the objectives are, the main objective, as I said, is the impact behavior under impact, but the first objective is the drop height and strength tension evaluation. After that, I will be doing some effect of compressive strength, bar spacing, bar diameter, some mesh location, and I will change after the verification with the numerical study or analytical studies. Also, I'm doing during this first paper part. So I will be also doing some numerically investigation for like the support conditions and geometry, because they can be in different geometries. Like, as I said, like there are some curved seawalls as well, not just vertical seawalls. That's the next step. And we will see a chance to, as I said, to develop simplified design equations that can predict the impact behavior of GFRP-reinforced seawalls. When I look at the literature review, I've seen that there are several factors affecting those. That's why I selected those parameters that I just mentioned, such as drop height, concrete strength, and reinforcement layout, and those bar diameter and spacing. And there are some several factors. As I said, the seawalls are in marine environment, and their support conditions are like cantilever type. That can change their behavior, and the soil presence as well can affect. So these are kind of things that I will be doing later. But when we look at the, in general, the mechanisms and mode of failure modes under impact, there is usually two types of failure. The first one is the local failure, and the second one is the overall global failure. When we talk about local failure, that's usually about the transmission of stress waves. And when we talk about the overall response, usually it can be a combination of local and a flexural type of failure at the bottom of the panels. So this type of seawalls, behavior is usually expected under impact loading. In this research, I am focusing on low velocity impact, which is below the 10 meter per second, but high velocity impact also can be done in other research as well. I've seen people are doing like missile type of impact behavior, but we are just focusing on low velocity impact in this research. The failure behavior can change, as I said, due to the overall local failure. What we expect is to have some maybe spalling or scabbing. It could be like perforation in the structure, or punching type of failure, or overall type of response. I would like to give you a general information about my methodology. So what I'm expecting from my drop height study is like a mode of failure analysis, impact force, acceleration and velocity, and maximum displacement and strain. There will be also some analysis part that has to be predicted and calculated. That's about energy absorption and dissipation and strength tension. When it comes to our design, our seawall design, as you can see on the left-hand side, it's just simple one-way slab that we have planned according to as the first step of this project. So the size of these panels are 1,000 to 1,000 millimeter in size, and the thickness is 125 millimeters. So when it comes to reinforcement details, we are using GFRP reinforcement in these panels, as you can see on the right-hand side. So the bar diameter I'm using in this study is 10 millimeters, and the nominal area is 71, and you can see also other mechanical and physical properties here. We reinforce these plates, doubly reinforced, so there is not just single reinforcement. So there is one at the top and one at the bottom, and we have 25 millimeters concrete cover. And we also placed some strain gauges in the reinforcement as well to measure the strain of the GFRP bars. The effect of drop height, as you can see, this is my test setup, and we have some different drop heights from 1 to 2 meters to change the energy levels that change the impact energy and the impact velocity. So we are testing them under impact from 1 to 2 meter, and we also do a reference sample for under flexural loading to analyze the strength relation after impact, because we will be doing also, we have done actually the flexural loading after these drop heights, which is a complex process that also no one has actually conducted in the literature. After impact, what is the strength retention of these panels? So that's also the second part of this study that we've done. The test setup, as you can see, the impact is on the left-hand side. You can see this drop hammer is around 300 kilogram, and we have some equipment to measure the strain, and the DIC for the deflection, and data logger for the false recordings. So we are using a plate here, which you can see this on the corner, right corner. That is our force assembly to distribute to force evenly and also protect the force sensors from a very high impact that 300 kilogram is causing on this structure. So, and also after this impact testing, and also I would like to mention how we actually measure the drop height. We have a special equipment here to measure the drop height between the panel and the hammer tip, sorry. So after this, we have done some post-impact flexural testing, which I will be talking about later. So the preliminary results and discussion part, I would like to first start with the impact. The effect of drop height on the failure behavior, as you can see from 1 to 2 meters, we have some global flexural cracks at the bottom. And we have some diagonal cracks next to the corners, and we have transverse cracks concentrating usually in the middle, and due to the impact being at the center of the panel. What I observed from here is up to 1.5 meter, there was no local failure, type of failure at the top surface. But after that, at the 2 meter, we have some a local crack here showing a local type of failure. So this also can be observed at the bottom of the seawall. Here's another big hole at the bottom. So the failure mode and crack pattern and propagation is different for different drop heights. So I would like to also mention about my results here. As you can see, from 1 to 2 meter, I calculated the impact energy, total force we recorded from our force sensors, the impact velocity and the deflection results, and the GFRP strain. So the deflection results, I will talk about them in the next slide, why there are variation or not a linear trend in the deflection and force. I've seen that in the literature, the research shows that failure mode under dynamic loading is very different than the static loading, and that can be influenced by inertial loads due to the acceleration and flexural stiffness due to the spring stiffness and damping load due to the energy dissipation. So these are my results for force, deflection, and strain. As you can see, the force didn't increase up to 1.5 meter and then dropped after 1.5 meter at 2 meter drop height. And my deflections results also surprisingly less at 1.5 meter, which after I analyzing this, I see that there is a relationship between the stiffness of this panel at 1.5 meter that showed a different trend than other drop heights. So I will talk about them, like what are my understanding from this preliminary discussion of these results. So failure mode changed with varying impact energy. Via drop height, the failure mode was only governed by global failure up to 1.5 meter due to the flexural cracks at the bottom, and no local damage was observed due to the perforation, pelling, scabbing, or crashing or cracking. So 2 meter drop height, we can see that caused an additional local concrete crashing failure near the impact point at the top surface of the seawall panel. And this changed the failure mode from only global fracture to local crashing failure. And crack propagation increased generally from 1 to 2 meter. However, there was differences in the pattern, and the deflections increased from 1 meter to up to 2 meter, but dropped at 1.5 meter. The structural behavior and failure mode is actually influenced, this panels influenced by the flexural stiffness of the structure and some damping and inertia force of the structure. And maximum force increased in general from 1 to 2 meter. However, it didn't follow a linear trend. The total force recorded reached a peak at 1.5 meter due to the increased impact resistance and stiffness of seawall panel, showing less deflections, but then it increased at 2 meter drop height. And highest GFRP strain was recorded at 2 meter drop height due to the GFRP rupture. I have to further analyze energy dissipation for why this trend happened in the force and deflection to evaluate this GFRP reinforcement and concrete behavior in terms of energy. And I would like to also give you a little bit more information about flexural, post-impact flexural behavior. That's, as you can see, my flexural testing only, and up to 1.2 meter, we tested these tested samples already under flexural loading as well. In general, the failure mode it was shear failure. So I will just give you a little bit overview of my results, and for the bending load, deflection, strain, and strength tension. Sorry if I'm rushing a little bit because I'm trying to finish it on time. So the impact flexural, post-impact flexural results can be seen here. Usually the trend of this flexural load deflection and comparison of maximum deflection drop height and also drop height with the maximum load strain behavior I talk about in the next slide. So what I observed from here is a failure pattern showed that the main failure mode was a shear failure under flexural loading compared to flexural failure under impact loading. The highest flexural deflection was observed at no impact, but compared to this reference panel that we have, post-impact flexural deflection is reduced from 1 to 2 meter. This means impact loading has already caused some deformation in the panels up to a certain level during impact testing, and 2 meter impact drop height had caused the highest damage during impact loading. So when we're comparing to flexural deformation of the reference panel, the highest reduction in flexural strength was observed at 2 meter. And post-impact flexural strength in general reduced from 1 to 2 meter. However, the trend didn't follow a linear decrease. Peak post-impact fracture strength was recorded at 1.5 meter drop height, and this was closest to the peak bending flexural load of the reference panel at no impact. This means it showed higher stiffness and higher resistance, and post-impact flexural strength then decreased at 2 meter drop height. In terms of GFRP strain, and this in general, it's also matching with my deflection results, decreased from 1 to 2 meter. The highest post-impact flexural strain was observed at 1 meter and the lowest at 2 meter, showing reduced post-impact flexural deflections. So from our comparison, we can say that flexural strength tension after the impact of 1.5 meters, flexural strength tension after the impact of 1.5 meter, the drop height, this was the highest, while it was the lowest at 2 meter drop height due to the, as I explained, the higher stiffness and resistance of this panel specifically. So further work, these results present preliminary research data and should be further analyzed before publishing. Thank you so much for your time. If you have any questions, please proceed. Thank you so much.